Let's start with this problem for the flux, okay? So the problem says, water is flowing through a cylindrical pipe of radius r. So I'm going to draw the pipe. So this is a cross section of the pipe with radius r. Let's assume that water flows fastest at the center of the pipe with a speed v0. So I can draw the speed of water is v0 at the center. Yeah. And it slows down to 0 at the walls of the tube in a linear way. And what I mean by that is that the velocity of the water is going down linearly until it reaches 0 at the wall. Okay? And the same here. And of course I'm drawing a cross section, but this would be a cylindrical pipe. So different radiuses would have different velocities. Okay? So the velocity of water follows this pattern, which is actually similar to what happens in an actual pipe of water. So the water at the edge cannot flow because it has friction against the pipe, while in the center it flows fastest. So I ask you to, well, first I say the mass flux density of water in this tube can be approximated by this function here. So to calculate this function here, I just did you know that the flux density, so here we called it F, is the density multiplied by the velocity, which is a function of position, right? So here I just substituted a linear equation for the function of position. So I said that the velocity as a function of position is equal to v0 times 1 minus rho divided by r in the direction z hat. So how did I know this? Well, if you substitute rho equals 0, so we are in the center. By the way, notice that I tilted my axis such that maybe this is x and this is z. Okay, so what is normally up now is right. Yeah, so that the cylindrical coordinates, so that the polar coordinates are dealing with the cross-sectional circle here. So if you substitute rho equals 0, you are on the z-axis, and then the velocity is equal to v0 z hat. So you get v0 z hat when you're in the z-axis. As you approach the surface of the pipe, the walls of the pipe, rho is increasing from 0 to r. So when rho equals r, this is equal to 1. So 1 minus 1 is equal to 0. So the velocity is 0. Okay? So basically I wrote here the equation for the velocity as a linear equation, and then I just multiply that, which is here, by k, which is the density of the water molecules. Okay? So F in this case, so instead of calling it sigma like in your previous example, I've called it k, the density. So now F is k times v0 times this linear equation in the direction z. So that is the mass flux density of water. Okay? So the mass flux density is telling us how much water per unit area, per unit time, and in which direction is flowing at each point. Very good. So as you see here, I'm saying K is the density of water and rho is the radial cylindrical coordinate. Calculate the total flux of water through the pipe per second. So we need to calculate the total flux through a surface like this one. Okay? So how do we do that? So the total flux will be equal to the surface integral of f dot ds vector. Okay, that will be the flux integral that we need to calculate. So we are going to follow the steps in the recipe. First step, parameterize the surface. So we have done this many times, so we are parameterizing. So let me draw the axis now straight way up, x, y, and z. So we have our pipe along z, right? And water is flowing in the positive z direction. So we have to parameterize this disk here. Okay, so this disk is easy to parameterize in cylindrical coordinates, right? So r, we will have two parameters, which is the distance from the z-axis rho and the azimuthal angle phi, and this will be equal to rho cosine phi, rho sine phi, and then z we can set z equals 0, because the flow on this tube, on this pipe, does not depend on where we are along the pipe, so we can choose any value of z. For example, z equals 0, which is this surface here. Okay, and the limits that define this disk are going to be rho between 0 and r, where r is the maximum radius of the pipe, and the azimuthal angle goes between 0 and 2 pi as usual. Okay, so that's our first step. Second step is to find ds. ds vector. So I would do it by geometrical intuition. Geometrical intuition. So the ds of this circle, if I try to draw it here, so we have this surface here, which is parameterized by the radius and by the angle. So this is the mesh that we're creating, right? So one of these ds's is the same ds as in polar coordinates, when we use polar coordinates, yeah? So I know that the length of ds, the scalar ds, is equal to rho d phi, okay? But now I know that the vector df, and by the way, now you see why I insisted so much at the beginning of the module, never forget the arrows when you are writing a vector, because then you would confuse things such as the scalar ds and the vector ds, okay? So the vector ds is just going to be the scalar ds, but in the direction normal to the surface, which is z hat, okay? So I know that ds is just rho d phi z hat. Okay, so you can find it by intuition. If you don't like doing it by intuition, you can look it up on the table. So let's see how we would do that. Let me go to the table. So this is the table given in the exam. We are using cylindrical coordinates, and our two parameters are rho and phi. Therefore, dz is a constant, so dz is 0. So therefore, this is 0, this is 0. So we are only left with this, rho d phi z hat, which is exactly what we found by geometrical intuition, okay? Because I looked at ds for cylindrical coordinates. Fine? So you can always use the table. But maybe you forgot or you lost the table. You printed it and then you lost it. So what can you do then? You could also calculate it. And the way you would calculate it would be like this. So ds is equal to partial of r with respect to rho cross partial of r with respect to phi times d rho d phi. Okay, so you would calculate the partial derivatives of r, and you have r over here. So you have to calculate the partial derivatives of this with respect to rho and with respect to phi. So what do you get? You get a vector. So with respect to rho, you get cosine phi, sine phi, and 0. Cross product, partial of this with respect to phi. So you get minus rho sine phi, rho cosine phi, and 0. Okay. Now you have to do this cross product. I'm not going to do it, but you can see that you will get the typical sine squared plus cosine squared equals 1, and eventually you will get that this is equal to rho in the z hat direction, plus 0 in the x hat and plus 0 in the y hat direction, times d rho d phi, which brings you to exactly the same ds vector as we found with the other two methods. Okay? So you can see that you can choose any of the three. Once you are an expert, you will directly do it by geometrical intuition. That's, I can guarantee you. In the meantime, either try to look it up or calculate it. Okay? Very good. So now we found ds. So what is the third step now? Is to evaluate the integrand at the surface. So what is the integrand? The integrand is f dot ds. And we know what f is, and we know what ds is. Okay, so the integrand is f dot ds, and I'm going to substitute. What is f? F is this function here, kv0 times 1 minus rho over r z hat. Don't forget that f is a vector, please don't forget it. Dot ds, and ds is also a vector. And what is ds? ds is rho d rho d phi z hat. Okay, so now we have, remember, you have to do two things. Make sure that any x, y, z that appears on f, you substitute it by rho and phi, so you can only use the parameters, or constant. So k is a constant, v0 is a constant, r is a constant. The only thing we have is rho, which is one of the parameters, so we are fine. We don't have to substitute anything. Everything is already substituted. But secondly, you have to remember to do the dot product. In this case, this dot product is very easy because you have z hat and z hat. So the dot product is just 1, z hat dot z hat is 1. And therefore you just get a scalar, which is k v0, 1 minus rho over r, rho d phi. And this is a scalar. There are no more unit vectors. So as promised, the sanity check is to check that this is indeed some function of the two parameters, rho and phi. And this is indeed a function of rho and phi plus constants. So this is ready to integrate. And the fourth step is the easy one. Calculate the integral. So this is a double integral. Flux is equal to the surface integral of f ds, which above we have written as k v0. Maybe I can expand the bracket, so rho minus rho squared over r d rho d phi. And then we have to set the limits. So the limits for rho are in the first integral here. They are 0 to r. And the limits for phi, which is the second integral, the outer integral here, are 0 to 2 pi. So now we just have to evaluate this integral, which is relatively simple. We can take the constants outside. Then we can apply separation of integrals because this is a function of rho times 1, and you could take 1 as a function of phi. So remember, when you have a function of rho times a function of phi, you can split the integral into 2. So you can keep the function of phi and integrate it between 0 and 2 pi, and then the integral with the function of rho between 0 and r, which is rho minus rho squared over r d rho. Okay, so this is the integration that you have to do. So this first integral is 2 pi, and this second integral is 1/2 rho squared minus 1/3 rho cubed over r between 0 and r, which is equal to 1/2 r squared minus 1/3 r squared. Okay, so this is 3/6 minus 2/6, so that's 1/6 of r squared. So this 1/6 gets multiplied by the 2 pi, so you get pi over 3. So the final answer is k v0 pi over 3 r squared. Okay, and that is the final answer for the flux of water on this pipe. Okay, so this was a nice example where you had water flowing not evenly, so the flux was not constant over the surface, and yet you can still calculate the total flow of water on the pipe by doing the flux integral, which we did following all the steps, and we arrived at this. Okay, so it's interesting that this would be 1/3 the amount of water that would flow on the pipe if there was no friction with the walls. Yeah, so if the velocity of water was the same throughout the whole pipe, so the arrows had the same length, then obviously the flux would just be the surface multiplied by f, so that would have been pi r squared times k v0. Yeah, but here we got the same, pi r squared times k v0 divided by 3. So the effect of the walls slowing down the water slows down the total flow of water by 3. So that's an interesting consequence of this calculation. Okay, see you in the next example.